Engineering 305, example problem 7.5. A beam is loaded and supported as shown. Actually, it's on the next page, but I copied it, so I got it both. Write the equations for shear force and the bending moment for any section of the beam. We have to do a graph which shows the shear at every section of the beam and the bending moment at every section of the beam. So do it for the interval AB, BC, and CD. All right. So if you look, you can see that things change. Things are the same from A to B, things are the same from B to C, and there's a point change at C, and then they're the same from C to D. And actually there's a point change at A and a point change at D. So if we're going to do that, the first step that we had to do was we had to section it, and we had to create the free body diagram for the stuff on the left. So what that would look like, and I'm starting this incorrectly, but you'll see it. I'm going to start with, okay, here's my beam, and at point A, I've got that force, and here's my section. Maybe I'll section it in red. And right away, I hope you see the problem. I don't know. This is the reaction force at A, and I don't know what that is. I don't know what that is. So our first thing, and I knew this when I gave the directions, when I did that in the lecture, the first thing we have to do, prior to what we did in the directions in the lecture, the first thing is solve the free body diagram. Solve for all reaction forces. All right. So here's my system, my free body diagram. And actually, I've got the wrong pen. I've got my beam. And I've got a reaction force at A, and then I've got a reaction force, and I'm following their language, so this is the reaction force at D. I'm even going to follow their colors, and that is I've got a distributed load, and I will try to be consistent that the distributed loads are red. I did this when I used the whiteboard in the classroom too. I would grab the red marker. And then I've got a point load. I've got a point load at C there. And so now I can define some points. Here, this is B. And I've got my point load at C. And then we could put dimensions on all this. But ultimately, I'm going to get back to something that looks exactly like the picture that's on the screen. So how do I go about solving this? Well, the easy thing to write down is the sum of the forces in the y direction is equal to the reaction at A plus the reaction at D. Those are my two unknowns. And then I've got this distributed load, which is 400 pounds per feet, and that's 6 feet long. So that's going to be plus, and it's a negative 400 pounds per foot, and that's times 6 feet. And I put the units right on there, one, because we're stressing units now, but also because you can see if you just throw down the pounds per feet, your units aren't going to match. The units on reaction at A are in pounds, and the units here are in pounds. So really the units for this have to stay in pounds too. All right, and then I've got one more term, and that's this force at C. That force at C is 2,000 pounds. That's minus 2,000 pounds force. Do I have everything else? No, I've got it. Okay, so that gives me one equation, reaction at A plus reaction at D, sorry, not B, plus reaction at D is equal to a minus 2,400 pounds from the first term and a minus 2,000 pounds. So a minus 4,400 pounds. Okay, that doesn't solve for the reaction at A or the reaction at D, but that's okay. We just now have to go use our sum of the moment equation. I'm going to get rid of the picture for now. Sum of the moments equal to 0. It's not moving. It's a static situation. So where do you want to sum about? The worst place would be C. Okay, let's sum it around A, and then I can solve for the reaction at D, and then I can go back to the other equation and get the reaction at A. So some of the moments about A, I don't have anything. Then I get my distributed load. So I know that's gonna cause it to. Let's put a coordinate system here to help a little bit. It really won't. X, Y. But because that's going to go Y into X, I know that the moment from that is negative. And now let's figure out, let me put that figure back on. I know the force of that. It's 2,400 pounds. Do I know where the centroid of that is? Absolutely. It's in the middle of that area, right? Because it's a constant. So that's 6 feet long. So 3 feet from B is where that's effectively acting. All right. I don't know if you can see my mouse. I don't know about that. Anyway, it's 3 feet from B is where it's going to be acting, but that's 5 feet from the beginning. So it's minus 2,400 pounds times 5 feet. All right, and then I also have, I'm going to put a plus, but it's not a plus. Changing to black because that's how I drew that force. I've got 2,000 pounds. Actually, and I'm going to put a negative because this is a plus and negative. It's also going to cause that, right? Right hand rule. It's going to cause that to go down. Almost knocked my microphone off. And the distance away there, I got to look at the picture again. 6 feet away. 6 feet away. And then I've got plus the reaction force at D times the distance away. And that distance away is 8 feet. Eight feet. So that would tell me I know that RD is in pounds too. 0. Let's just rearrange it all at the same time too. We're going to do RD is equal to, I'll keep my red, minus 2,400. That's going to be 12,000 foot-pounds. That's the first term. The second term is also 12,000. Huh. Interesting. Oh, but those are now both positive because I moved them to the other side. Plus and plus. And then I divide that whole thing by 8 because that's the distance. That's the distance that I had there. Divide by 8 feet. And I've got 24,000 foot-pounds divided by 8 feet, and that's equal to, I'm supposed to remember to look up once in a while, 3,000 pounds. That wasn't bad. Didn't use the calculator, didn't hit pause. I like that. That's good. RD is equal to 3,000 pounds. And RA plus RD, oh, you know, if you look at that, we got to look at that up there again. See, look at that. RDA plus RD, it's a positive 4,400. Who's my partner on that? It's like euchre, right? You count on your partner for one. Well, all right. RA plus RD is a positive 4,400 pounds. So that means that RA is equal to 1,400 pounds. Let me get that written down. And so now I have a complete free body diagram that looks like this. My reaction at A is 1,400 pounds. I have 400 pounds per square foot there. 2,000 pounds at C, and then reaction at D. I'm going to move that. Oh, grab the wrong thing. I'm going to move that to the top of the page. And we'll keep working the problem. We'll keep working the problem. So, I got to get that to the right spot. There we go. So, now that first step, maybe it's the second or the third one, but we section the beam. We're going to section the beam. So my beam now looks like this, that. I've got a 1,400 pound force there. 1,400 pounds. I'm going to section it here. And this is point A, and point B is somewhere over here. So this is anywhere in this section, anywhere along here. If I would do the sum of the forces in the X direction, well, and then what we've got to do is I put a dummy force on here. This is V. That's my reaction force. That's my reaction shear. And I've got to put M. That's my reaction moment. Okay. Now, the way I drew those on, those are both positive. Do you see that? They're both positive. That is, that reaction, that force would make that would make that side of the step go down, and then I could walk downstairs, and that makes me happy. So I'm smiling. I'm happy, I'm smiling. It's a positive day. The same thing, that moment is going to create an inboard, that's going to create a happy face. I'm smiling. It's positive. So some of the forces in the X direction are equal to, I've got a plus 1,400. That's this force on the end. And then a minus VR. And I'll put a coordinate system on here too. X, Y. And so what I see for anywhere and that's true for anywhere in that section from A to B. Wherever I would split it, that would be my free body diagram. So I don't want red. VR is equal to 1,400 for X is greater than A and less than B. Yeah, that maybe doesn't quite make sense, but you get what I mean. In that region from A to B, for any X, VR is equal to 1,400. That's that reaction force. Let's keep going. Let's not hide it that much. I guess I want that a little bit. We're going to move it over here just to get my mug out of the way. Some of the moments, well, my moments equal to, I'm going to write that because I don't want, I'm going to write that about, we typically consider writing it around that point. And it'll make sense why as we do more sections. It'll make more sense in the next section where we've got the distributed load and it makes a difference. The sum of the moments are equal to, well, I've got this 1,400 pounds, and that's going to cause Y to go to X, so that's a minus 1,400 times X times whatever the distance is that I'm away from that cut. So this distance here, right, the distance to that point is X. 1,400 times X. And then I've got nothing else except MR, which is going to be, that's going to be positive, plus MR. So that's equal to 0. So MR, that reaction, the reaction moment at that face is equal to 1,400 times X for X is between A and B. So now what I want to do is start plotting this stuff because that was what we're going to be asked for. I want to start plotting this stuff. So if I were doing a shear diagram, I'm going to have positive and negative shears. I would start out at 1,400, and for this is A, and I've got B here, and I've got C over here. Actually, the distance from B to C is, it's 4 feet, so maybe I should go a little bit farther. C and then D. For this section, it's right here. And then I got to put another plot together. Let me get rid of that. That's not what I want. That's what that looks like. And then I can put a moment diagram together. And my moment is, it starts at 0. And I got to get my distance right. How far away is B? Oh, it's only 2 feet. So it's 1,400 times B. So this goes up to 2,800. And my units here are foot-pounds, but it goes, and that it gets there at B, which is here. And that's 2,800 foot-pounds. This was 1,400 pounds. All right. That's A to B. Now I can go do B to C. And see how these problems are big. They just, because I just do it again and I do it again. So I don't need to assign a ton of homework or a ton of problems because you're going to repeat the same problem. We're on this example problem. We're going to repeat the same thing 3 times. So here's the next section. There's my beam. I'm going to split it anywhere here. And now I'm adding a distributed load here. I've still got my reaction force, 1,400 pounds. This is 400 pounds per foot. All right, I get a reaction force. I got my reaction forces that I'm adding here. That's VR, MR. And now I'm going to take my sum. So for this next section, sum of the forces in the x direction are equal to 0 are equal to, well, I have a positive 1,400. And then I get a minus 400 times, now my x is still measured. That's my x coming all the way from here. And so the distance that I've added to this weight is x minus 2. Right? Because I don't have any of that for the first 2 feet. So when I get to here, it would be really that, if you want to say, yeah, it's just a coordinate transformation, but it's kind of important. That's that x minus 2. So starting at here, it's 400 pounds per foot, but I subtract the first 2 feet if I start my coordinate over there, which I'm going to do. Coordinate transformation. And then do I have anything else? Yes, I've got this minus VR. So that tells me that VR is equal to 1,400 minus 400 x minus 2. Okay. I can plot that. I can go back up here. 1,400. Well, that's the value that it was there. So that's good. That equation matches up at B. That's good. If I'm drawing an equation, I want it to be consistent. And at B, it has the same value from the left as it has from the right. That's how we have a continuous equation, if you remember that. So, and then minus 400 times x minus 2. So I'm going to go, let's see. Oh, sorry, I got to start up here. So this is 4 feet away. So here's 2 feet away. So I had to go down 800. So this is still at, so if I go, that's 1 foot away. So I'm going to be down there. Well, let's see. I'm going to cross it 3.5 feet away. Actually, right there. I'm going to go to there. This is at 5.5 feet is where that crosses. Because 3.5 times 14, 3.5 times 400 is equal to the 1,400. So that's that line. And this line continues to there. At that point, the value is going to be, it's 4 feet away, so it's 1,600 pounds. So this is at minus 200. All right. And then I got to do my moment equation. I got that. Now I got to do the moment equation. So now some of the moments in the x direction are equal to 0, are equal to, well, it's 1,400 times x. Because I'm 1,400, I'm x distance away from that. And then I need to subtract. Well, I know what my shear, oh, this is hard. How much weight do I push down? Well, I push down 400 pounds times whatever distance I am minus 2. This is the weight. So that's the weight. And then how far away does that push? Well, whatever this distance is, it pushes halfway. So that's going to be x minus 2 over 2. Do I have to add to the 2 there? I have to think about that. No, the distance that I'm going to push is there. X minus 2 over 2. Nope, that's what I'm doing. So now I'm gonna be careful here. I'm gonna say this is my force, and this is my distance. Okay, here's how I got the distance, and because this is confusing, the distance is from the cut edge back to there. And so the distance all the way back to here would be x minus 2. And so this distance here is x minus 2 over 2. I remember. It's been a while. And I want to make sure, I want to try to make sure that explanation is pretty clear. Now, do I have anything else to add? Yes, I do. I still have plus this reaction moment at the end, that dummy moment that I add at the end to figure out what that is. And so then, sorry, I can already see it. That's supposed to be a negative. Is that supposed to be a negative? No, this is supposed to be, that's supposed to be a negative, and this is supposed to be a positive, right? Because I'm trying to spin around this point. I'm trying to spin around the cut. So that's going to cause, this is going to be, that sign is now correct. And that sign is now correct. Yes. And that gives me that the moment in R is equal to is plus 1400x plus 400. Well, I'm going to simplify this. 200 x minus 2 squared. All right, so 1400x plus, well, then I should probably like multiply that out, so that becomes plus 200 x squared minus 4x minus 4, and then I'm going to still have a 1400x out here. So this is going to be equals, sorry, you guys are letting me make mistakes. This sign is wrong here when I copied that down. So this sign is wrong. Minus. So here we go. Zoom, and there it went. Minus 200x squared minus, well, wait. I'm going to say plus 1400 minus 800x minus 800. And now I can simplify that. I had to do that because I'm just making a lot of little silly mistakes. Minus 200x squared plus 600x minus 800. Now, that equation is valid for x between b and c. And I'm going to change that between x is between 2 and 6. Now, what happens at 2? At 2, I've got 2 squared is 4, so I get minus 800 Oh, that's a minus 4. You guys totally let me down here. I got sine errors all over the place. I got to go back through this whole thing. You really make me want to just start the video over, but that is such a nuisance then to edit these things. So here we're finding all of my mistakes. The x minus 2 squared is x minus 4x. That becomes a plus. Right there, mistake number 1. All right, then when I go on, that does become, that's a positive. That flipped signs, so that's okay. So that's a minus 200x squared. Then this becomes a plus, not a minus. So now this becomes 2200x. There's our second mistake. And then the last mistake is I've got, let's see, I've got a plus 4 and a minus 2. So that becomes a minus 800, and I'm probably good with that. All right. So now let's evaluate this at 2. Oh, my goodness. Probably just need dinner. Maybe a little bigger yet. At x equals 2, I get minus 200 times 4 plus 2200 times 2. Can't even write 2200. That's a 4400. Minus 800. It's really a minus 1600. Right? 400 times 2 is another 800 minus that. So that gives me a plus 2800. Well, now I know I got it right, because that's what I had from, that's my limit from the right is equal to my limit from the left. Now, the bigger problem is I've got this funky curve going on. You see that? I've got a minus 200x squared, a plus 2200x. I've got a funny curve. So let's evaluate this at, I really should evaluate it at 2 different points so that I know what this looks like. I really ought to evaluate this at x equals 5.5. Why do I say that? Well, because that's where my shear went from positive to negative. That's where it crossed that 0 point. So that's important. And then I should also evaluate it at x equals 6. Well, let me do that a sec, and then I'll tell you the numbers, and then we can go on. But that'll save us some time. And actually, I can go get a beverage because my throat's getting a little parched. All this yakking. Yak. So pause it. I'm going to solve those. I'll be right back. I know you guys know I'm a nut, so I calculated the answers, but actually I threw it into Excel, plotted the equations, and so you get, instead of this lousy graph that I'm starting to build up here, because I could draw that line and it would go like this, and I would hit a 0, and then it's going to start coming down, but there you go. There is a high quality curve. Here's where it crosses at 5.5 feet, so that's cool, and there you go. There you go. Now we've got one more section to do this for. And that is, I'm going to, it really looks a lot like the previous sections, except, here you go, squiggle, because we're starting over. My beam now looks like I've got a load there, and I've got a load there, and then I've got a distributed load here up to the point where I cut that thing off, and boom, 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 boom. We're getting good at this, I hope. Coordinate system here, x, y. I'm summing the moments about this point. I've got to put on my dummy load VR and my dummy load MR in order to keep this thing stable. Now I can run through it. Sum of the forces in the y direction are equal to, that force was 1,400 pounds. I feel like I'm forgetting something. So, nope, 1,400 pounds. And so that's equal to 0 is equal to, and that's going to make the steps go down. So I'm good with that. That is 1,400. And then I go to the next thing I get is to that, and that's minus the 400 pounds per foot times x minus 2 feet, right? And then I'm going to keep going minus, when I hit C, this right, this is point C, this was point B. When I hit C, then I subtract. If I'm beyond C, then I subtract this load, which was, it's a 2,000 pound load. First time I've worked with that. So that's a 2,000 pound load. And then I also subtract VR when I get to the end. So now my equation for VR is equal to, because VR went to the other side, everything changes sides. VR, everything stays the same. Sorry. So it's 1,400. And I'm going to put pounds all the way. I should have put a pounds there. I'll put pounds all the way at the end. 1,400 minus 400 times x minus 2 minus 2,000 pounds. The whole equation is pounds. That's my equation now for VR. So that's going to take, really, if I look, I could rewrite this to be equal to, 1,400 minus the 2,000. That's just going to give me a 600, a negative 600. And then it's minus 400x, but it's a plus 800 there. So that's going to be 200 minus 400x. So, and this equation is valid for x between 6 and 8 feet. So let's think about that. Well, at 6 feet, my answer is 6. So it's minus 2,400. It's minus 2,200. So if I go back to this plot, this goes way down here someplace to minus 2,200. But then it continues the same slope, right? The slope is still minus 400x. So it's just going to continue that same slope out to 8 feet. Now, I say, every time I've said this, I've said, well, my equation, my numbers should match from the left and from the right. Well, this is different. I hate to say that, but this is different. The reason this is different is because I have a discontinuity in my beam. When I look at my beam, I've got a discontinuity there, that I've got a point load. And that point load causes a change in my shear equation. So that is real, that there's a discontinuity that's showing up there in my equation. So I know I said it needed to be consistent, but it is consistent. I have a point discontinuity. It shows up there. Let's keep working my moment equation. You know my moment equation is going to stink, don't you? Because it's going to be some of the moments in y about the cut, about the cut are equal to, I've got 1,400, it's negative 1,400 times x. And then I've got to do, once I hit B, then I start incrementing, then I add this other load, which is going to be, that's going to make it go positive, though. So it's positive 400 pounds per foot times the x minus 2. That's how much of it, wherever I am, it's all of that distance minus the n 2 feet. And then the distance it's applied is still the x minus 2 over 2. And then I've got to add this force from C, which is, that's also going to make it go down. So plus 2,000, and then times that's x minus 6, because that's the lever arm for that. And then I've got to put, of course, I got to put the MR on there. So that's a positive MR. All right, and then rewrite that equation. That's all equal to 0. So MR, oh my goodness. MR is equal to 1400x times, this I've seen before. I'm going to just put minus, well, you know what? If I look up above, I'm going to get 1400. Sorry, I got to go all the way back up here. I got 1400 minus 200 x minus 2. Well, that's because I simplified it. This is exactly the same. This equation is the same. And then I put that one extra term on for the point load at C. So I can start by saying, look, I've got this as my starting point. And then I just have to add to it rainbow sprinkles. So I'm going to get rid of this. And I should have just cut and paste this. Can I do that? I can. Well, lasso. And I'm going to copy. And I'm going to paste. And then I'm going to put, now my MR stays on this side. So this is moving across to the other side. So then I got to put minus 2,000 x minus 6. So that's going to be a minus 2,000x. So, okay, so equals minus 200 x squared. I've got plus 2200x and a minus 2000x. So that's going to give me a plus 200x. And then I've got a minus 800 and I've got a minus 2000 times 6. So it's actually going to be a plus because it's a minus minus. That's 12,000. That's 800 minus 800. So that is going to be a plus 11,200, and my unit behind all of this is pounds. All right, now hold on. So I should keep what I was going to threaten to do is evaluate this at, right? I should evaluate this at x equals 6, and I should evaluate this at x equals 8. I should evaluate this at x equals 8. 8 squared is 64 times 200. What's 64 times 200? I'm going to get the calculator out. Let me evaluate this at 6 and at 8, and I'll write down the answers. They'll go right here. MR is equal to, ready? All right, so I went and evaluated points. I threw everything, continued to put it into my spreadsheet, calculated points. And here's what we got is I calculated my moments at 6 feet and at 8 feet, and I calculated my shears at 6 feet and at 8 feet. And you do get a discontinuity when you use the equations from the left or from the right, and that shows up there. That's what that discontinuity looks like. And that makes sense if you start plotting all of those points. If you start plotting those points, you get, yep, my shear comes along. I just have the one shear at 1 acting on the end. And then I get into my red zone, which constantly decreases the shear until all of a sudden this event happens. Well, that monster shear comes in and knocks that slope down, down at a discontinuity. And then my slope continues to decrease because that load continues to truck along. What does my moment look like? Well, my moment looks like my moment. My moment looks like that. I have a moment And it can, because that distance gets farther and farther away, that moment starts to increase, but then that positive shear, and it starts to come back until all of a sudden that goes negative. Now, once I cross at 5.5 feet, then that moment starts to decrease. And then once my shear goes really negative because of that point load, it decreases at a dramatic rate. You can still see curvature though here, can't you? You can still see how that's because I've still got that minus, is it 200x squared term? Yeah, that term is still there, so there's still some curvature to that. And then I wind up at 0. I have no moment at the end. And that makes sense because my beam is in equilibrium and I can't have anything going on at the end. But if my beam was in equilibrium, get rid of all my scratch on here. If my beam is at equilibrium, why is it that my computer locked up? Why is it that that value is at minus 3,000? Here's why. Technically, that's not quite at 0, but it's really, 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 really close. But again, you've got to remember, this equation for shear is when I approach from the left. And when I approach from the left, it's going to be different than the right. Why? Because I have a point load going on at D, which is that positive 3,000 value. And that is going to take that's going to take that right back up to be 0. So if I drew the full chart, it would look like that. But that's happening at a point. Anything beyond here is at 0 if I approach it from the right. If I approach it from the left, I'm at minus 3,000. If I approach it from the right, because of the point load, which is that shows up in the free body diagram, I get back to 0. So there you go. Good answers. And there is example problem 7.5 with some mistakes for us, for some sign errors going on and some other stuff that we caught along the way. Long example problem. Sorry about that. I hope you're enjoying your weekend. You see that it's Saturday night at 7 o'clock, Halloween, and I'm working these problems? I should be trick-or-treating. I could dress up like a college professor and go out and do my gig. I could be bagging candy all over the place. All right, you guys take care. There's more to come. Don't worry about it.